Ladies and gentlemen, hello and welcome everyone to our final presentation concerning the automatic classification of the preliminary diabetic retinopathy stage for the final phase of the Dell Envision the Future competition. So first, we're going to start this presentation by answering two main vital questions. What is diabetic retinopathy and how is it caused? And what made us choose this specific topic? And the answer to the first question would be that diabetic retinopathy is simply a retinal eye disease that is caused by too much sugar in the blood over a very long period of time. And to be more specific and concise, diabetic retinopathy is caused when the blood vessels behind the retina get weakened over time and get damaged, which causes new abnormal blood vessels to grow at the back of the eye. And the problem is that these abnormal blood vessels not only leak fluids into the eye, but they can also cause major problems. As for what made us choose this specific topic, well, after deeply searching and studying diabetic retinopathy, we came down to these four main points. The first point is that diabetic retinopathy is a very sensitive case, and if we wouldn't be able to accurately detect it, it could eventually evolve and lead to more severe consequences and complications such as total blindness. The second point is that after thoroughly analyzing diabetic retinopathy even more, we found out that according to studies and statistics, 1/3 of people suffering from diabetes are also expected to be diagnosed with diabetic retinopathy, which eventually increases the number of people at risk. The third point is that it's very paramount for us to detect diabetic retinopathy at a very early stage so as to be able to prevent any serious complications in the future. And the final point would be our ability to create a reliable assistive systems for the doctor that can ensure delivering accurate results. The following scene demonstrates and strongly depicts the world through the eyes of a normal person. A non-diseased person has the ability to easily perform his daily routines and enjoy his life. However, many others simply can't because of diabetic retinopathy. It feels different when you're a diabetic retinopathy patient. Life becomes tougher and much harder with each upcoming day, and the small details become more vague and ambiguous. Going through the simulation, we were somehow able to convey and picture the world through the eyes of a diabetic retinopathy patient.
After discussing why diabetic retinopathy was our priority, now it's time to discuss the need of using an automatic system. Actually, using an automated system offers way more features over the currently available solutions, and we can summarize them in 5 main points. First of all, the early detection of the disease was our first priority due to its importance in the treatment process. The usability and user interface of our system was one of our main concerns to offer a system that is easy to be used by each and everyone. In order for the system to be applied, it is a must that the output results are reliable, and this was our core point. Depending on the market research we have made by the beginning of this project, the system is expected to find high acceptance by the expertise in this field, especially that it offers a low running cost unlike many of the currently available solutions. So by implementing this system, we are aiming for improving and minimizing the shortage in the currently available solutions, especially regarding the system's efficiency and its output accuracy.
Going through our system overview, which is starting with uploading the images to our system, the system passed through different stages. First, pre-processing, where we normalize all the images to be all equal sized. Then the main process stage takes place, where we classify the input data and train the system. Finally, the last stage, which is the result stage, where the doctor views the result containing if the patient has diabetic retinopathy or not. If yes, the system view which stage the patient is in. According to our system overview, in our block diagram we divided our system into 6 modules. First, login and sign up module, where each user log into his own portal. then data acquisition module by taking images from each source and upload it into our system, then data manipulation module where we normalize the images, then detection and classification module where we use our classification model to classify the patient stage, then the report and summary module where the system generates a detailed report after uploading the both left and right eye images. At last, the user interaction module which contain all user function as viewing report, create, read, update or delete. Our core system cycle consists of 4 different phases. First phase is the input image phase, where the system take an input fundus image from the patient. Then the second phase is the pre-processing phase, where the system pre-processes the images before starting the next phase, which is the classification phase, where the system detect and classify the disease level for the input image. Finally, and the fourth and the last phase is the result phase, where the system display a printable detailed report with the result of the classification process. Now we are going to preview our main demonstration and how the doctor interact with our system. First of all, the doctor logs into the system using his specific username and password. Now he is directed to his home page. The doctor can mainly upload a fundus image or view the list of the previous report for each patient. For example, let's start by uploading both the left and the right fundus image, or even only one of them, to be proceeded during the classification process. In our case, let's upload the left and the right image and see the full demonstration of our system. And now, let's click on Classify Images. Now the system starts loading, or in another word, start calling the Python script in the backend, which are responsible for applying all the required pre-processing techniques and classifying the input images. Finally, the results are ready to be viewed by the doctor in a detailed form, with the percentage to each class, and this is surely will help the doctor in taking the right decision. Next, these are the results are displayed in a printable report form, which is more friendly for the patient. The digital form offers as well the ability to add some written prescription before printing. Another situation is viewing the list of reports for a specific patient, where some of his or her report were made by another doctor. In this case, the doctor can edit or delete only the report made by him, not by anyone else. And this was a short demo presenting the doctor side of the system.
As for our plan, we had 4 main activities. First, with gathering and analysis the data, which mainly included studying the research done previously and to specify our main objectives. Second, system design, which included mainly stating the system requirements and to apply all the software engineering concepts and techniques to make sure that those requirements will be met. Third, system development, which included implementation of the system by the means of developing, testing, and integrating system parts. The fourth and the last activity was system testing, but as mentioned before, due to the current pandemic, we settled for using different datasets only. To test the model and observe how it deals with unseen data, we split the dataset into training and testing. We trained the model with the first portion of dataset, then we tested the output model with the second portion which the model haven't seen before. To make sure that our model is generalized, our primary plan was to test it with an external samples collected from our ophthalmologist, but due to the current pandemic, we changed the plan to just test the model with a different dataset. The last step of evaluating our system is to compare it with the previous work done. In doing that, we have 2 main criteria. First, the number of datasets used to build that model. Second, the achieved accuracy. As for the dataset, the previous work ranges between 35 and 50,000 images, and clearly we outstanded that number and reached 88,700 images, keeping in mind preserving the balance between classes as we previously explained. As for the accuracy achieved, the previous work ranges between 70 to 82%, and our system also crossed that line by achieving 84%. Also, we have to mention the sensitivity. The previous work ranges between 40s and 80s, while our system achieved 81%, which is close to the highest value, but we didn't plot the comparison between sensitivities because not all the previous work have mentioned it.
So in conclusion, the main goal of the proposed system is to be able to thoroughly enhance the detection of diabetic retinopathy, the applicability of the system based on market research, the system impacts the social and industrial aspects of life, innovative features are also used to solve critical problems and issues, and finally, we are still investing more time and effort as we believe there is still better, which leads us to planning the system's future work. When it comes to the future work, we came down to these two main points that would eventually and hopefully enhance our system. The first point or method involves trying out new techniques and models that would eventually improve the system's performance. And the second method involves trying out real-life data from real-life diabetic retinopathy patients so as to be able to prove the system's applicability and measure its performance in real life.